Hey guys, it's Chili here. Welcome back to Advanced C++ Tutorial 2. Today we're looking at the dot product. Now this guy is the MVP of vector operations. You use them all the time, super useful, super cool, super sexy. It's going to be a good time. And in order to learn this guy, we got an interesting little problem that we're going to be tackling. It's a little bit of physics. So we're going to do some rigid body physics with some rebounding, calculating the velocity of rebound. Now, if you think back, if you remember to Fartanoid, we had a ball and it collides with walls and with bricks. But the walls and bricks that it collides with, their faces are always going to be horizontal or vertical. And when you have a situation like that, it was very easy, right? Because the rebound, basically, if you break down the velocity into its x and its y, and you're rebounding against a vertical wall, all you do to get the velocity of the rebound is you take this and you flip it this way. And now you've got a vector that is the rebound vector. So you keep the component that's parallel to the wall, you keep it the same, and the component that is going into the wall, you flip it in the other direction. It was very easy, very intuitive. Now, what we want to do today is we want to do that same thing, but we want to be able to calculate the velocity here with an arbitrary inclination of our wall. And what people will often do when confronted with a problem like this is they'll say, well, okay, I know what reflection, how it works. This angle is going to be equal to this angle. So all I've got to do is, I guess calculate this angle and then this angle, and then I can get this angle's the same, and then I just have to use some trigonometry to figure out this vector. And you're doing a lot of cos and a lot of, like cos -1 or sine -1 or whatever. And it's not it's complicated, but it's not the hardest. But the real bad thing is that these operations are incredibly slow to do on a computer. So we would like to avoid them if possible. And what happens when you use vectors and dot products to calculate this instead of angles is you don't have to use any cosine sine, none of this stuff. You do it with a few simple multiplications and addition, subtraction. It's super fast. And it's a different way of looking at the problem, and it can be much cleaner to solve a problem with vector operations instead of with angles. So, now that I've set the stage, what the hell is a dot product? All right, let's take two vectors here, j and I hat. And the hat here, when you put a hat on a vector, that means that the vector has a length of 1, so it's a normalized vector. So we want to calculate j dot I hat. How do we do that? Well, the first step, we want to visualize this. Let's draw a line that is in the same direction as I hat. So this is the line of I hat, we'll call this. And to calculate the dot product, what we're going to do is we're going to project j onto this line. What does that mean? Well, it means we're going to draw a line from the tip of j down to the line of I hat, and we're going to draw it such that the angle is 90 degrees. And this gives us the projection of j in the line of I hat. Okay? Pretty simple to visualize, right? Now the length of this projection here, that is just exactly j dot I hat. So the dot product, it just gives us the length of the projection of j into I hat. And one thing you notice about this is very interesting. Dot product is operation between two vectors, but it yields a scalar value. So that's the first thing to know about dot product. It's a vector operation that yields a scalar. Interesting. Some other things to note is basically what this is doing is this is giving us how much of j is going in the direction of I. Okay, so if we look at a different vector here, let's take a look at a vector. We'll call this one k. All right. Now, if we do k dot I hat, what do you think the value is going to be for this? Well, if we project this down 90 degrees, k is already 90 degrees to I. So the projection is just going to be right at the origin. The length of that line segment is 0. So we can see that things that are perpendicular to I, the dot with them is going to be 0. because none of this is going in the direction of I. It's all going orthogonal to I, or perpendicular to I. None of it is going in this direction, so the answer is 0. Likewise, if we put a vector going in this direction here, I don't know, I'll just call this one M hat, M. What do you think the dot product is going to be? Well, it's going to be this length here, whatever that is, but it's going to be negative length because it's going in the opposite direction of I. So the dot product tells us how much we're going in the direction or in the opposite direction or not at all. It's very important information. So the next question is, how do we actually calculate this dot product here mathematically? Well, if we know this angle here, theta, then we could use SOHCAHTOA to calculate that. So SOHCAHTOA tells us that cos theta is equal to the adjacent over the hypotenuse. So we want to know the adjacent. That's this one, the angle or the side that's adjacent to theta, and we know the hypotenuse. That's just the length of j. And we know theta, so we should be able to calculate this. So the hypotenuse is equal to the length of j. So if we do a little bit of algebra, we know A, which is equal to the dot product. So we can do j dot I hat, which is just A, is equal to h, which is just the length of j, times cos theta. And there you go. So your dot product is just the length of j times cos theta. So let's take a look at this demonstration applet here. You can check it out at this address. So we've got two vectors, a and b. B is a length of 1, so that's our unit vector, our normalized vector. And then I'm moving a around. And you can see here, the yellow line gives us the projection of A in the line of B. And we can see here the calculation for that is A cos theta. And we can see that our applet is telling us that that's equal to A dot B. Very interesting. Now, up until now, all we've been doing, here we can see a negative, here we can see it goes down to 0. Now, up until now, what we've been doing is we have been having one vector that's free, but the other vector has to have a length of 1. But what if this vector had a length that wasn't unit length? How does that affect the result of A dot B? Well, let's scale B up. Let's double its length and see what happens to A dot B. So we want to keep the same angle, 43.8 degrees about, but we want to make the length of B twice as long. So let me do that. So here I've doubled the length of B about while keeping the angle right about the same. And if we look at A dot B, it has doubled. So the length of the projection is still 1.2. That doesn't change. But A dot B doubles when you double the length of B. So what is the actual formula for the dot product then? Because it's not just dependent on the length of A, it also depends on the length of B. And the answer is quite simple. For any two arbitrary vectors that both have any kind of length you want, the product is just going to be, or the dot product is just going to be the length of A times the length of B times cos theta, right? Because if you double the length of B, dot product doubles. If you double the length of A, dot product doubles. So it's the product of their lengths times the cos of the angle between them. And this is the angle version of the dot product formula. Now you might be saying, Chili, I don't get the big deal here. You said that we could do our bullshits without having to use cos and sine, but now you've done a big cos and sine in here. Well, here's the deal. There's another way to calculate the dot product. It gives you the exact same answer, but that doesn't use trigonometry. And it's very simple. Let's say A and B are two-dimensional vectors. The dot product is going to be AX times BX plus AY times BY. And there you go. It's that simple. And this will give you the same result as this complicated thing here. But it's very simple. It's just a couple multiplies and an add, and that's all you need. and you can solve complicated problems that conceptually require angles without needing to know the angles. You solve them only knowing the components of the vectors, and that is incredibly powerful. This power of the dot product allows you to think in terms of vectors and to diagram out your problems and solve them without ever needing to worry about angles. And also what you can do is sometimes you might derive a problem and it has angles and cos when you derive out its formula, and you can rework the formula and then substitute in the dot product instead of these cos and sine and theta. And you'll see me doing that in 3D fundamentals, but today we're going to work purely in vectors to solve the physics problem. Now, one of the most common uses that I have for dot product is to figure out how much of one vector is going in a certain direction. So the way we do that is we define our direction with a unit vector in that direction. So let's define some basic ones. So y hat will be the unit vector going in the y-axis, and x hat will be the unit vector going in the x-axis. And let's say we want to know how much of j is going in the x direction. Well, we could just do, j dot x hat is equal to, and here x is 1, 0, so we're going to do let's see here, 2 times 1 plus 3 times 0. And that will cancel out the y component, and we're just left with 2. So here we can dot product with x hat to get the x component. We could dot product with y hat to get the y component. You might be saying, oh, whoop-de freaking do, Chili. We could just look at the actual components of the vector and get the x component of the y component. We don't need to do this song and dance, and you're correct. But now, let's say we have another vector, unit vector, that's in an arbitrary direction. Here, we'll call this one k hat, and we want to know how much of j hat is going in the direction of k hat, and this will let us do it. You can't inspect it, you can't just look at the numbers here and tell, but with the dot product you get that information super easy. So it's very common to dot one vector with a unit vector to get some kind of length component. Very common. So now let's use this information, this technology, and solve the problem of a ball rebounding off of a wall that has an arbitrary inclination. So, quick recap of what we did in a Fartanoid. We had a ball, it was hitting the wall at a certain velocity, and to rebound it, basically, we just flipped the component of the velocity that was going into the wall. So if the wall was vertical, the component into the wall is the x component, so we just do x is equal to negative x. X is equal to negative x there. You flip that, and this is now the velocity that the ball is going to rebound off the wall with. So it's very simple, and we want to do the same thing with our arbitrary inclination. We want to flip the part of the vector that is going into the wall. So first we have to calculate, well, what part of the vector is going into the wall? Okay, so let's do this step by step. All right, so basic setup with relevant information. We've got a ball, it's going towards the wall. It's got a velocity, okay? The wall is defined by 2 points, P0 and P1. How do we start? Well, let's get a vector that gives us the direction of the wall. And that vector is just going to be, let me see here. We'll call that vector W. And W is equal to P1 minus P0. That gives us W, which is going to be a vector that, goes up to here. Now we want to get, because the wall is going to be our direction that we're going to be projecting onto. So we need a unit vector in that direction. That's simple. We'll call that W hat is equal to W divided by the length of W. So just normalizing W, that gives us W hat. So now we have, W hat here. Good. Now let's get the amount of component of V that is going in the same direction as W. So to visualize that, that's going to be, if this is V, that is going to be this projection here, right? So we calculate that with our good old friend, the dot product. That's going to be V dot W hat. So that gives us the length of the projection in the direction of W, the length. But what I really want here is I want the vector component in this direction. So I want a vector that has the length of the projection and is moving in the direction of W. So how do I do that? Well, if I have a length, if I have a unit vector and I want a vector that has a length L in that direction, all I've got to do is multiply by that unit vector. So this will give me the vector component of V that is going in the direction of W. That's the part of V, the vector part of V that is going in the direction of W. And let's call this K for lack of a better thing that I can think of. So K is the part that's going in the direction of the wall, the parallel component. But we want to know the part that is going into the wall, right? That's the perpendicular component, all right? So if we know the parallel component and we know the entire velocity, velocity is equal to the parallel component K plus the perpendicular component J. So let's call this J for now. All right. Now we know K, we know V, we don't know J, but we want to know J. So it's just simple algebra, right? J is equal to V minus K. Beautiful. Okay, so now we know the component going into the wall. Now we want to flip that. How do we flip this component? Well, let's look at it this way. Well, V is equal to J plus K, right? If we add negative J to V, what happens? Well, adding negative J will just cancel out the component going into the wall. And now V will be running exactly parallel to the wall. Stop that. Now, if we add negative J times 2, we'll actually be flipping V, right? Because adding once, negative J once, subtracting J, cancels it out. Subtracting it twice, flips it. And now V will be going in this direction, which is the direction of rebound. There you go, you've got the answer. So let's call the rebound vector here U. U is equal to V minus 2 times J. There you go. What is J? Well, J is V minus K. Okay. And that is V minus 2 times V minus V dot W times W. W hat. And we can simplify this a little bit. If we distribute this 2 here, we get V minus 2V plus 2 times V dot W times W hat. And so these guys, you can just collect them together and you get U is equal to 2 times V dot W hat times W hat minus V. And there you go. This is how you can calculate the rebound velocity dependent on the points of the wall and the initial velocity. And it's not a complicated operation for the computer to perform. It's just some multiplies, some subtraction. It's very simple. And I hope you guys found this derivation, pretty straightforward, easy to follow, easy to visualize, because it's a very visual thing with these vectors. But if you had trouble following, if you find this just very difficult, don't worry about it. It takes a little time to switch your brain into the mode of thinking in terms of vectors, which is part of the reason why I introduced them early. I wanted to get you just familiar with the basic, addition, subtracting, scaling operations. But this dot product stuff also takes a little while to get into your brain. So just stick with it. Keep using vectors. Keep trying to think in terms of vectors. Maybe read up on some other materials, tutorials, do problems. Get this vector stuff into your head, because once you can think fluently in terms of vectors, it's going to make a lot of this stuff a lot easier to understand. Vectors are an incredibly powerful tool for describing and thinking about spatial and geometrical problems. One thing I want you to note and just keep track of, this here is an incredibly common meme in vectors. To get the component, the amount of one vector in the direction of a unit vector, and then to take that and to scale the unit vector by that amount. This is a super common vector meme, and I want you guys to remember it. But that's gonna about do it for today. Stay tuned for the next video, part 2, where we're gonna take this theory and we're gonna put it into practice by creating a simple little physics simulation. Until then, I hope you liked this video. If you did, please click the like button, it helps a lot. And I will see you soon with some more advanced C++.